Hello students, in the previous lecture we covered the concepts of moment of inertia of the plane area. We also discussed the standard formulae to be remembered and how to remember the formulae for various components and their applications. We also covered three problems of moment of inertia of the composite area about the centroidal axis. Now we are coming to the next problem. In this lecture we will cover uh, 4-5 more problems on composite area, and I'll also cover one problem of moment of inertia of area under curve. Right now, to begin with, first problem of this lecture: find centroid of the given unequal I section shown in the figure. Also find moment of inertia about x-axis and y-y centroidal axis. You are given with this unsymmetrical I section where this is the bottom flange. This bottom part is 200 into 15. This is 15 into 200 and this is 16 into 15 mm. You can see that this section is symmetrical about YY centroidal axis. So YY centroidal axis can be marked based on symmetry. Can you see that? Moment of inertia about axisymmetry IY will be calculated directly as IXX will be calculated indirectly. So I took this point as reference axis OX and OY. Right? We have taken this dotted line indicates that I have divided the composite area into this is one rectangle, 200 into 15. Second one is this part. Here dividing line is must. This is 15 into 200. Third one is 60 into 15. This is YY centroidal axis, which we get it by axis of symmetry. Due to symmetry, I have shown it. X bar is 200 by 200 mm. X bar is 100. Right? To find Y bar, you'll have to use the formula. Y bar is A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3. Component number 1. This is your X reference axis where Y bar will be measured. This is component number 1. Its area 200 into 50. Y coordinate of centroid of this component is from X axis 7.5. 50 plus. Second component is 15 into 200. Its centroid is 100 mm from this bottom edge. 100 plus 15, 115 is Y coordinate of centroid of second component. Third component, 60 into 15 its area. Its centroid is here. It is at what distance from x-axis? 15 plus 200, 215 plus 7.5, 222. Divided by A1 plus A2 plus A3. A1 area is 200 into 15. A2 is 200 into 15. And A3 is 60 into 15. You get 82.28. Total area of the given I section is denominator. This is capital A. That is, we mention it for total area or equal to summation A is 6900 mm square. Now, students, first we'll have to find IOX because x-axis will be found indirectly. Moment of inertia about x-axis centroidal axis of the given I section will be obtained indirectly since it is centroidal axis other than axisymmetry. So let's find first OX. Component 1 is touching the base, or component 1 is resting, its base is touching the x-axis, so moment of inertia can be written directly about base. Base formula can be applied. Base formula 200 into 15 cube by 3. This is for component 1. For component 2, base is not touching the x-axis, so we have to find first about parallel centroidal axis. This is its parallel centroidal axis. Moment of inertia of component 2 about parallel centroidal axis, what? 15 its width, 15 into 200 cube by 12. Plus area 15 into 200. Square of the distance 100 plus 15, 115 square. That is component 2. Component 3, 16 to 15 cube by 12 plus area 16 to 15. Again, you have to transfer it to x-axis. 15 plus 200, 215 plus 7.5, 222.5 whole square. So this way, moment of inertia of component 1, 2, and 3 are obtained about OX axis and added up so that you get moment of inertia of the whole area about OX. You add it up. But we know that IOX is equal to IXX plus AY bar square. IOX we have substituted. IX is needed. Area is of the I section is 16900 into Y bar is 82.28 whole square. You get IXX. Then you want to find IYY. How will you find IYY? Moment of inertia of this unsymmetrical I section about axisymmetry YY will be obtained directly. Can you see that component 1? Its centroidal axis is coinciding with YY, parallel centroidal axis coinciding with YY. So directly we can find moment of inertia of component 1 about YY directly 15 into 200 cube by 12. Component 2, again, its centroid is centroidal axis coinciding with YY, that is BH cube by 12, B will be 200 into 15 cube by 12. Third component, 15 into 60 cube by 12, it's directly moment of inertia of the component 3 about YY. Add them up, it comes 10.326 into 10 raised to 6 mm raised to 4. So this way we find moment of inertia of the given unsymmetrical I section about XX and YY centroidal axis. All right. Do remember that you need to find the moment of whenever you have to find the moment of inertia about the centroidal axis of the composite area, your first task will be to mark the centroidal axis of composite area. Either you mark with your knowledge of axisymmetry if it is there, or otherwise by centroidal. Now let's move to the next one. Second sub. Determine the moment of inertia of the Z section shown in the figure with respect to x-axis and y-axis. Can you look at the diagram? X-axis and y-axis are shown. These are not centroidal axis. So there is no centroidal working in this problem. There is no centroidal working this problem. Directly you'll find the moment of inertia of the given Z section about OX and OY reference axis. So need to draw the diagram again. Then we take this as component 1. This dotted line shows that your component 1 is of width 20 centimeter and height 5. Then again a dotted line here which shows that this component 2 is of width 2.5 and depth 15. Component number 3 is of width 10 and depth 2.5. All right. Now you have to find moment of inertia of the three components about OX and OY axis and then add them. Now component number 1 is its base is touching the x reference axis OX. So base formula can be applied directly to find moment of inertia of component 1 about OX. What is that? BH cube by 3, 20 into 5 cube by 3 plus. Second component, its base is not touching OX, so you cannot apply any base formula. So first find moment of inertia about parallel centroidal axis. Parallel centroidal axis moment of inertia will be what? BH cube by 12. B is 2.5 into 15 cube by 12 plus area 2.5 into 15. Then transfer it to OX. What is distance between OX and its centroidal axis? 15 ka adha, 7.5 plus 5, that is 12.5 square. 5 plus 7. Then we come to component number 3. Component number 3 also we have to find first moment of inertia about parallel centroidal axis. What is that? 10 into 2.5 cube by 12 plus area 10 into 2.5 square of the distance. What is that? 5 plus 15, 20. 20 plus 1.25, 21.25 square. That is component number 3. Add them up, you get it. IOX 11302.08 centimeter. Then we come to IO. When we talk about IOY, component number 1, you have to find first about parallel centroidal axis 5 into BH cube by 12, 5 into 20 cube by 12 plus area 5 into 20. Okay, distance between two parties 10 plus 7.5, that is 17.5 square. Component number 2, parallel centroidal axis moment of inertia is 15 into 2.5 cube by 12 plus area 15 into 2.5, square of the distance 7.5 plus 1.25 whole square. Component number 3, its base is touching reference axis y. So we can apply moment of inertia about base formula directly. Base is BH cube by 3, 2.5 into 10 cube by 3. So this way we add up moment of inertia of each component about OY and you get the moment of inertia of the whole area about 7682.3 centimeters. So you have observed that when moment of inertia about reference axis asked, there is no centroidal working involved. All right, you don't need to find any centroidal distance, no need to mark any centroidal working. Moment of inertia of an entire area about reference axis is obtained directly, as in this problem about OX and OY we have found. All right. Now, so far the problems we have come across were involving square primarily. I have already discussed 5 problems. These are all important problems what normally we come across in moment of inertia. Now we are going to move to the other components will be involved. Like in this problem, next problem, I'm involving triangle. Just making you to recollect the triangle formula from the sheet. Moment of inertia of the triangle about centroidal axis parallel to base is BH cube by 36 and about center base it is BH cube by 12. Again I repeat, base formula for any component is applied only when the base is touching the axis about which moment of inertia is required. Now he is asking in this problem, obtain the moment of inertia of the following lamina about x and y reference axis. This is x reference axis, this is y reference axis. Both the reference axes are not centroidal axis, so no centroidal working is involved. How you can take this area bound by this continuous lines? You can take this as a rectangle of width 100 and depth height 50. Then you can take up this triangle minus and this triangle. So here we have drawn the component 1. First I am taking OX. Component 1 is rectangle of base width 100 and height 50. So BH cube by 3 is the rectangle about base. Base is touching the reference axis X, so base formula can be applied directly 100 into 50 minus. I am taking second component. Its base is not touching the X reference axis X, so you have to use parallel axis theorem. First, find moment of inertia about parallel reference at central axis. BH cube by 36. B is 30 into 50 cube by 36 plus area BH by 2, 30 into 50 by 2. Distance between the two axes 50 minus 50 by 3. Then minus for third component. Third component, it is 30 into 20 cube by 36 about parallel central axis plus area 30 into 20 by 2 into distance between the two 20 minus 20 by 3. You have to take the distance between parallel central axis and reference axis OX. 20 minus 20 by 3 whole square. So this way you get the moment of inertia of this area bound by continuous lines about OX. Then we find about OY. This rectangle is again, its base is touching reference axis Y, so we can find moment of inertia directly. That is 50 into 100 cube by 3 minus this triangle. This triangle's base is also touching reference axis Y, so that is BH cube by 12. B is 50 into 30 cube by 12 minus this triangle BH cube by 36. First, you find moment of inertia about parallel central axis as base is not touching reference axis. So, moment of inertia of this triangle about this central axis BH cube by 36, 20 into 30 cube by 36 plus area B into H by 2, 20 into 30 by 2. Distance between this central axis and reference axis Y is what? 100 minus 10, that is 90. So, moment of inertia of component 1 is taken positive. Component 2 is negative since it is being subtracted. Component 1 is bigger. Component 2 is being subtracted. Similarly, component 3 is also being subtracted. So this way, moment of inertia of the area bound by continuous lines is obtained as component 1 minus component 2 minus component 3. So IOY comes out to be 14.11 into 10 raised to 6 and 9 raised to 4. So in this problem, I have introduced you to the triangle component, how to apply the moment, how to apply the formula for moment of inertia of the triangle about base and also about its central axis. Okay. Now, in the next problem, I have incorporated quarter circle and semicircle. What I have incorporated? Quarter circle and semicircle. What is asked in the sum? He is asking me to find the moment of inertia of this shaded area about X and Y reference axis. So how will you take the shaded area, students? You have to take it square plus semicircle minus quarter circle, right? No centroidal working involved because moment of inertia is required about the two reference axes. Come to this side. So I'll take it this square as component 1 minus component 2 quarter circle and third is semicircle. Now component 1 is square about OX. So this square is base is touching reference axis OX. So directly base formula can be used 20 raised to 4 by 3 minus quarter circle. For quarter circle, base is not touching reference axis. So parallel centroidal axis is this. Moment of inertia of the quarter circle about centroidal axis parallel to base is 0.1098 r raised to 4 by 2. So 0.1098 r is 20 raised to 4 by 2 plus area of the quarter circle pi r 4 by 4. Distance between the two is 20 minus 4r upon 3 pi, the whole square. That is your component number. Come to component number 3. This is semicircle. Its parallel centroidal axis is this. Moment of inertia about this centroidal axis, which is axisymmetry, is pi r 4 by 8. You understood in the formula sheet? Pi r 4 by 8 plus area pi r square by 2. Distance between the two axes is 10 plus 2. You get it by taking the moment of inertia of component 1 positive, component 2 negative, component 3 positive. You get it 22.551 into 10 raised to 3 centimeter. Then we come to moment of inertia of the shaded area about OY. Square about base 20 raised to 4 by 3. This quarter circle, its base is touching the reference axis OY. So base formula can be used directly here. Minus pi r 4 by 16. That is moment of inertia of the quarter circle about base. Radius is 20. Then we come to semicircle. Moment of inertia of the semicircle about OY is required. So first we'll find moment of inertia about parallel centroidal axis. What is that? Moment of inertia of the semicircle about centroidal axis parallel to base is 0.1098 r raised to 4 plus area of the semicircle pi r square by 2 Distance between the two axes 20 plus 4r upon 3 pi whole square. So this way we find moment of inertia of the shaded area about 2y 115.34 into 10 raised to 3 centimeter raised to 4. As the dimensions are in centimeter, moment of inertia unit will be centimeter raised to 4. Now, next one. Calculate the moment of inertia of the rectangular lamina of dimension A and B with respect to diagonal. You have a rectangle of width B and height A. He is asking moment of inertia about its diagonal. This is one of the diagonals I have taken. Drop the perpendicular from A on this diagonal, its height is h. Drop the perpendicular from point D on this diagonal, height is h. So first we'll find, see what we'll do that, for finding the moment of inertia of this rectangle about diagonal BC, I'll find moment of inertia of the triangle ABC about diagonal BC and moment of inertia of the triangle BCD about BC. Length BC will be square root of A square plus B square, right? We write this angle as theta. Same, this will be theta. So what will be sine theta? In this, sorry, if this is theta, you want to find h. So h will be A sine theta in this triangle. In triangle AEC or AB. See, in triangle BC is what in triangle ABC. What is sine theta? That is opposite B upon hypotenuse. Cos theta is base upon hypotenuse. That is A upon A square plus B square square root. In triangle AEC, what is H? Is going to be A sine theta. H is going to be A sine theta. So moment of inertia of the whole rectangle about BC will be moment of the triangle ABC about BC, BH cube by 12. Moment of inertia of this triangle BCD about base is BH cube by 12. Now, we write 2 times BC into H cube by 12. 2 times 2 by 12. BC is what? We have found it A square root of A square plus B square into A sine theta ka cube. That is what is value of H. Now, just open out the bracket. Here, A cube we have taken out. 2 by 12, that is by 6. So, A cube by 6. Okay. Then square root of A square plus B square. Now, we are substituting the value of sine theta. Sine theta is what? B upon square root of A square plus B square square root. We substitute and we have to do its cube. What you have to do, by mistake, it is written as square, it is cube, right? This is a printing error. Now come to this side, A cube by 6, square root of A square plus B square. Here B cube, it will become upon, this will become A square B square, this is square into square root of A square plus B square. Here A square plus B square square root, here in denominator A square plus B square square root gets cancelled. So what do you get with A cube B cube upon 6 into in the bracket A square plus B square. This way, we have found the moment of inertia of this rectangle about diagonal. How we find moment of inertia of this rectangle about diagonal? You have just taken a moment of inertia of the triangle ABC about base BC and moment of inertia of the triangle BCD about base, and we add it up. So we find moment of inertia of the rectangle about diagonal. Okay. Now, we have introduced you to the components square, rectangle, semicircle, and quarter circle. In this problem, you will be introduced to one more component, that is circle, and of course isosceles triangle also. Now here he is asking you to find in this problem moment of inertia of the plane lamina about axis A. All right. Now here this is shaded area. You have to divide into simple components. If I put this as a dotted line over here, then this will be isosceles triangle plus rectangle plus semicircle minus circle. Now come to this side. This is semicircle with this dotted line. This is rectangle and this is triangle and minus circle. So how will you take it up? Component 1 is isosceles triangle. Component 2 rectangle. Component 3 semicircle. Component 4 circle. Mind it that none of the components is touching the reference axis. So you have to apply parallel axis theorem on each component. See, your entire shaded area is away from axis AB. So none of the component is touching axis AB, so you have to apply parallel axis theorem on each component. How you apply parallel axis theorem on each component? You have to find moment of inertia of each component about its parallel central axis and then apply parallel axis theorem. Like component number 1, it's a triangle of base width 90, height 65. So its moment of inertia about central axis parallel to base is BHP by 36. 90 to 65 by 36. Plus area is 90 to 65 by 2. Distance between this axis, central axis, and this is what? 40 plus 65, 105 minus 65 by 3 also. This is component 1. Now we come to component 2 rectangle. Its base width is 90, height is 80. So about central axis parallel to AB is what? 90 into 80 cube by 12 plus area 90 into 80. Distance between its central axis and AB is what? 40 plus 65 plus 40. 145 square. Come to component 3. This is semicircle. Central axis parallel to AB of the semicircle is central axis parallel to base. Moment of inertia of the semicircle about central axis parallel to base is 0.1098 r raised to 4. 0.1098 r. R is 70 raised to 4. Plus area pi r square by 2. Distance between the two axes is 185 plus 4 r upon 25 whole square. R is 70. Now you come to the circle. Moment of inertia of this circle about AB is required. So parallel central axis this. Moment of inertia of the circle about central axis pi r 4 by 4. Radius is 35. So minus pi r 4 by 4 plus area pi r square into square of the distance. 40 plus 65, 105 plus 80, 185 square. So this way we got moment of inertia of the shaded area about AB. We took triangle plus, rectangle plus, semicircle plus, and since it is a removed area outside the bracket, we wrote minus. So moment of inertia of the circle is removed or negative. Hope it is all understood. So we get moment of inertia of the shaded area about it is 400.78 into 10 raised to 6 mm raised to 5. Now, we have covered many problems, including all components, rectangle, square, circle, semicircle, quarter circle, triangles, right? Now, sometimes we have to find moment of inertia of area under the curve. Whenever moment of inertia of the area under curve is required, we need to take help of integration. We need to take help of integration, right? So in this, if area under curve is resting on x-axis, we have to take elemental strip, which is vertical. If area under curve is resting on y-axis, we take elemental strip horizontal. All right. And if area under curve is not resting on any of the two axes or resting on both axes, you can take strip horizontal or vertical. So once we mark the elemental strip on the area under curve, then we first find moment of inertia of the elemental strip using our moment of inertia of the about rectangle formula, of the moment of inertia of rectangle formula we are used. And then we integrate with appropriate limits so that moment of inertia of the entire area under curve is arrived. So this is what is written over. Now I'll just take one problem to give you the idea how we get the moment of inertia of area under curve. I'll just see that. Only one problem we are discussing. Find moment of inertia about x and y reference axis of the shaded area under the curve. So you are given this shaded area. This shaded area is resting on x-axis, so I should take elemental strip vertical. The equation of this curve is given as y is kx raised to n. This is a, this is b. All right. Now we need to take the strip vertical. In this strip, elemental dimension will be dx. Width is elemental, which is considered to be a distance x from the reference axis y. Height of this strip, which is substantial, is y. So what is the dimensions of this strip is? Width is dx, height is y. All right. Height is average height we take it. It is not taken up to top or bottom. We've taken up to the middle of that. So average height of the strip is y and its width is dx. So first we'll find the moment of inertia of this elemental strip about x and y axis. And then we'll integrate that expression with appropriate limits so as to get moment of inertia of the whole area under the curve. Now, equation of the curve, y is equal to kx raised to n, right? At point B, and this is the point B, where where at the point A, coordinates x coordinate is A, y coordinate is B. So I'm substituting the in the equation of curve x, A, and y. So substitute the value, you get value of k, b upon a raised to. So y is equal to b upon a raised to n into x raised to n. Moment of inertia of this rectangular strip about base will be dh cube by 3. B is dx, height is y, dx into y cube by 3. Moment of inertia of this strip about reference axis over diox is dx into y cube by 3. Moment of inertia of the rectangle about base. You want moment of inertia of the entire area under curve about base about ox, so you have to integrate. You are integrating with respect to x. If you are integrating with respect to x, limits will be along x. Lower limit will be 0, upper limit will be 0. So your finally moment of inertia of the whole area under curve about OX axis, IOX is equal to 1 by 3 y cube dx. 1 by 3 can be taken outside. Substitute the value of y. P upon a raised to n x raised to n. P cube upon a raised to 3n x raised to 3n. Integrate lower limit 0, upper limit a dx. You substitute the value of y. B cube upon 3a raised to 3n. It's outside the constant part. Integration of x raised to 3n will be x raised to 3n plus 1 upon 3n plus 1. Lower limit 0, upper limit a. B cube upon 3a raised to 3n. Put the limits. So this becomes a raised to 3n plus 1 upon 3n plus 1. A raised to 3n gets cancelled. So it becomes ab cube upon 3n plus 1. So this is moment of inertia of the entire area under this curve about x-axis. Now we have to find moment of inertia of this strip about y-axis. As this strip is a rectangle, it's not touching reference axis y, so I have to apply parallel axis. Moment of inertia of this strip about parallel centroidal axis will be y into dx cube by 12. Hope you understand. That moment of inertia of the rectangle about centroidal axis what dh cube by 12. B is y into dx cube by 12. Plus area is y into dx, and distance between the two axes x plus dx by 2. Dx by 2 is being neglected into x square. Now here dx is very small, so dx cube will be all the more small. So this term can be eliminated, neglected. So dioy is equal to y into dx into x square. Now if you want to find it for the whole area, you need to integrate with appropriate limits. Once again, you are integrating with respect to x. Lower limit will be 0, upper limit will be a. So 0 to a. X raised to n into x square into dx. B raised to n. This is x raised to n plus 2 dx. Lower limit integration 0. B raised to n. What is integration of x raised to n plus 2? X raised to n plus 3 upon n plus 3. And lower limit 0, upper limit. Put those limits b upon a raised to n into a raised to n plus 3 upon n plus 3. A raised to n gets cancelled. So a cube b upon n plus. This is what is moment of inertia of this area under curve about y. So student, this is just to give you the idea how you get moment of inertia of area under curve. Do remember that you need to take help of integration. First we take the elemental strip, find the moment of inertia of the elemental strip about the two reference axes about which moment of inertia of the whole area is required. Then integrate the expression with appropriate limits so as to get the moment of inertia of the entire area. All right, there are a few more problems given solved in my book, all right, which you can definitely refer if you want more in detail. Right, book is available on Amazon. Link of Amazon is given in the video description of this video lecture. All right, book has many MCQs, all right, or many solved problems are also given, even on area under curve also given, all derivations are given in the book. Please share the QR code of my YouTube channel with your friends so that they are also benefited with these free video lectures. There is no compulsion to buy the book to watch this video lectures. You simply share the QR code with your friends. Please do share it because it will help others also. Something what is being offered free should be definitely shared with others, right? If you buy the book, that will also be definitely worth. You'll get many more solved problems, derivations and all MCQs, you'll get it. Some practice problems are also, additional practice problems are also given. So with this, we have completed moment of inertia of plane area topic. All right, my next topic is going to be on virtual work. That is also there for VJTI and SPC students at least. It may be for other college, autonomous college also. Please check your syllabus and then only watch the video lectures. All these lectures which I'm taking these days are for autonomous college students. And your syllabus was already complete. Thank you.